Assalamualaikum warahmatullahi wabarakatuh. My name is Ahmad Shukri Muhammad. I'm from Electrical Engineering Section, a British Malaysian Institute, University Kuala Lumpur, Malaysia. I would like to present my paper, the three-phase 41 level matrix inverter based on modular multi-level converter half-bridge modules. Among the many types of inverters, the multi-level inverter is fast emerging as a popular choice in many industrial applications, from oil and gas, power plant to power quality devices. But the main disadvantage of the multi-level inverter is the high number of power switching devices needed in each design. Thus, they will increase the size of the overall inverter circuit and may increase the space occupied by the inverter in the system, and subsequently it also increases the power losses in the conducting switches. A matrix converter generally has three basic components: input voltage terminals, switches matrix, and output load terminals. The mathematical model of such arrangement for general matrix converter is the input voltage matrix, the switch matrix, and the output voltage matrix. A matrix converter is generally an AC to AC converter, so the input voltage and the output voltages are AC. Almost all of the available research literatures, the matrix converters are commonly a three-phase to three-phase conversion device. As we can see in this diagram, these are the input terminal and this is the input sources. So there are three input source or a three-phase input source into a three-phase to three-phase switch matrix, which then supply a three-phase output load. So it will be represented by a matrix of BAN, BBN, BCN equivalent to a matrix of SAA, SBA, SCA, SAB, SBB, SCB, SAC, SBC, SCC multiplied with a matrix of BAO, BBO, BCO, where BAN equivalent to SAA multiplied with BAO plus SBA multiplied with BBO plus SCA multiplied with BCO, and so on for VBN and VCN. Hypothetically, the matrix converter, as we have seen in the previous slide, the matrix converter inputs can be replaced with DC sources instead of the conventional AC sources. By timing the switches states similar to a multi-level inverter control strategy, the converter output waveform now is an alternating step waveform similar to a multi-level inverter output, albeit the output waveform is completely in the positive amplitude range. In order to reduce the output total harmonics distortions without employing filter, the input voltage can be increased greatly so that the rate of change of the output voltage dV over dt can be greatly reduced. The output phase can be set not only as a three-phase but also as a single-phase output, and liberally other output phases numbers as well. As we can see in this diagram, the plus side of having high output voltage level is the higher the output voltage levels, the lower the output voltage HD. So as we can see in this diagram on this table, as we increase the number of output voltage levels, the total harmonic distortion percentage will be reduced. The concept of modular multi-level converter was first presented by Prof. Dr. Rainer Marquardt, a former Siemens employee, in a patent filed in 2002. The three-phase modular multi-level converter circuit
and its half-bridge submodules are shown here on the right and on the left respectively. The modular multilevel converter is actually a cascaded half-bridge multi-level inverter. It's a single DC source configuration. Each submodule contains a half-bridge inverter with a dedicated DC source. In this case, a capacitor. Using a sequential switching strategy, the capacitors are charged using the common positive and negative DC buses and is charged to produce the step output waveform that indicates the desired sinusoidal waveform. However, the capacitors could also be replaced with independent DC cells in each module. The Matlab Simulink simulation shows the original multi-level modular converter submodule is not suitable to be used as the basis of the matrix inverter. This is because the switch modules can only show proper functioning capability and all the switch modules in the same DC bus have the same switching position. But whenever there is difference in switching conditions between two adjacent switch modules, the positive and negative buses will be short-circuited. This is caused by the negative DC bus line shares the same connection with the lower level output phase line. So whenever S2 is turned on, it will connect negative bus with the positive bus via the upper level negative bus and the turn on S1 switch of the adjacent switch module. To solve the problem, the half-bridge submodule circuit was modified. As we can see on the right hand side of the slide below, right hand side below diagram, there are two viable options available. The first option is to isolate the negative DC bus from the output line using another switch. Although electrically this is a very good solution, we will add another switch to the submodule, resulting 3 switches for every submodule and a huge 50% increase of total number of switches in the overall circuit, which defeats the main motivation of reducing the number of components. It can be observed that regardless of the switching status of the adjacent switch module, the positive and negative DC bus short circuit can be prevented by leaving S2 open all the time, whether S1 is closed or open. From this observation, the second option to solve the problem is by removing S2 completely from the switch module circuit. Effectively left the connection open circuit and completely isolating the output line from the DC bus line, as shown in the slide in the figure right below. This also reduces the switch count in each module to only 1 or a 50% reduction of total switch count in the inverter circuit. So obviously the second option is the best solution to the problem. The matrix representation of the proposed matrix inverter topology is shown here. So the input is VDC, while M represents the submodules, and then VEN, VBN, and VCN is the output of the matrix inverter.
The matrix inverter general topology. To make the converter output behaving similar to a normal AC source, i.e. operating in both positive and negative cycles, the neutral point of the matrix input will be moved to the center of the DC sources array. So, in this matrix inverter topology, the top DC source positive terminal when measured is equivalent to the peak output voltage, Vp, in each of the AC output phases, and the negative terminal of the bottom DC source in the DC source array when measured will be equivalent to the negative peak output voltage, negative Vp of the AC output, where M equals to 3, 5, 7, 9, 11, and so on in the odd increasing number. M equals to 2k plus 1, k equals to n minus 1 over 2. So k equals to integer starting from 1 in increasing fashion, 1, 2, 3, 4, 5, and so on until infinity. N also integer from 1, 2, 3, 4, 5 until infinity. And M times N is the total number of switches, where M minus 1 over 2 times VDC equivalent to VP. To validate the topology, a 41-level 3-phase matrix inverter is constructed in the Matlab Simulink platform in order for the validity and functionality of such topology to be tested and verified. Each of the ideal switches is replaced by a pair of cascaded MOSFETs connected together at the source. The bidirectional MOSFET switch has a drain-to-drain channel with a common gate terminal. The test parameters are VDC equivalent to 17 volt each, so that we can get VP equivalent to 340 volt. This will bring us to a single phase voltage output VRN equals to VYN equals to VBN equals to 240 volt. The three-phase voltage output VRY, VYB, and VBR equivalent to 450 volt. Nominal output frequency is set at 50 Hz. RL load series 47 ohm, 0.68 Henry for each phase, so that we get 47 plus J 4.27 ohm start connection output impedance. So this is the tested matrix inverter circuit. This is the matrix inverter matrix mathematical expression, and this is the switching table of the matrix inverter. The 41-level 3-phase matrix inverter output is shown above. The voltage total harmonics distortion, THDB, for red phase, yellow phase, and blue phase at the load terminal is 1.98%. The current total harmonics distortion, THDI, for red phase, yellow phase, and blue phase is 0.057%. This is way below the 5% limit set by the IEEE standard 519-2014 for harmonics distortion. As a conclusion, the matrix inverter concept and topology development has been presented. The matrix inverter combines the simplicity of a matrix converter topology and the operation of a multi-level inverter. Only one conducting switch is needed for the operation of each phase output. The validity and functionality of the matrix inverter topology has been tested by a 41-level 3-phase version of the proposed matrix inverter. The output is similar to the output of an equivalent multi-level inverter with a very low THD reading. Thank you for listening to my presentation. I hope you all enjoy my presentation. Thank you again.